Hello, CEP 637. So I want to provide this video just as a walkthrough of assignment 2, which is a review of topics from around NOVA. And I'm going to be doing this in SPSS just like you would. And I'm going to be giving you some commentary of what I'm thinking as I'm going through answering the question. So let's take a look first at what the assignment details said. Hopefully you've looked at the codebook file, which will help you really understand what these variables mean. And then you were presented with a question and were requested to use an ANOVA. And remember, an ANOVA, test differences in means between groups on some continuous variable. So in this case, the question was, what differences, if any, exist in students' mathematics scores, which in this data set you will be using a variable named PV1 math, based on how much they reported enjoying mathematics, which will be the variable ST29Q04. And then make sure to describe center spread shape, examine if assumptions for ANOVA are met, and include all the relevant output from ANOVA in your response. This is to get you into the practice of what you should be doing every time you are engaging in statistical analysis. These are the types of things you should always start with doing. And it's good practice to be pulling that relevant output in rather than just providing a list of all of the output. I want to see which output you're drawing on and how you're using it in your response. So here's the data set that you should have been able to download. There are two rows that were created in SPSS. These bottom two were not part of the original PISA 2012 data set. And we will talk later about how to create those. So these represent the z-scores for just the subset of countries in this data set, as opposed to SES, which was standardized across the entire set of 60 or 70 some odd countries. So in this ESCS is PISA's measure for SES, and it is 0 represents the average SES for the entire set of countries, whereas this SES down here, 0 represents the average for just the set of 6 countries that are included in this data set. And if you want to know what those 6 countries are, you can look back at the codebook to see. All right, but the variables we will be using this time around are PV1 math and ST29Q04. And I'm actually going to put after this, or in the label category here, I'm going to type enjoy math so that I don't forget that that's what that means. All right. Okay. And if we look back at the codebook file, you will see enjoy math has 4 levels in it. Strongly agree representing 1, strongly disagree represented by the number 4. So if we go back to the data set, in here it says values. We can actually put that in here. So a value 1, I'm going to put means strongly disagree and add it. This will help me make sense of this better later. 2 is disagree, 3 is agree, and 4 is strongly agree. And this is agree with the statement, I enjoy math. So if we look back at the code book here, the statement is I enjoy math, and then they had to pick one of these options, strongly agree to strongly disagree. So if we're trying to answer the question, and let's look back at it, what differences, if any, exist in students' math scores based on how much they reported enjoying math? The first thing we want to do is examine whether or not this is going to give us whether our assumptions are going to be met, and look at the center spread and shape, which helps us examine the assumptions. So actually first, I'm just going to look at PV1 math overall and see if there's any issues just with PV1 math. So if I do that, we're going to see, okay, so this first thing here we see that there's nothing missing, which that's not true for other things. And I'm realizing that I forgot to change this in plots to a histogram. I don't want to see that stem and leaf plot, and I want to see the normality plots. Okay. So we have the mean. There we go. It's taken a while to run it. A mean of 456. This is across all countries in the data set and regardless of how much they enjoy math. So this is not diving into those specific groups yet. A mean of 456. We have a median of 451. That tells us that it probably is a little bit skewed to the right. And if we look at the skewness and kurtosis values, though, those are quite small. So there shouldn't be any major issues there. Standard deviation of around 95 points. And a minimum of 85 and a maximum of 828. Quite a long range. And you can see there, it actually looks quite normal or symmetric. But you can see perhaps a slight skew on the right, slightly longer, but the QQ plot does not look like there's any issues. The points are staying relatively close to that line. And you can see from the box plot, there are quite a few outliers on both the low end of the scores as well as the high end of the scores. That could be something that's problematic. However, ANOVA is quite robust against deviations from normality, and those points don't seem too problematic to me, and they are real scores. So we're going to keep that in mind as we move forward. But this is what it looks like overall. The test of normality, the Kolmogorov-Smirnov test, produced a significant result. So this 0 here, which actually means that the p-value is less than 0.001, it means that the distribution is varying enough from normality that it seems to be far away. But the problem is that tests of normality do not work very well when there is a very high number of people in the sample. And you'll see up here there's 65,535 students across these 6 countries. So this is not very useful information. In fact, when a sample size gets that large, it is difficult even to trust any p-value. So we have to use additional evidence to make sense of whether or not that p-value is meaningful, which should always be the case, but it just becomes more important whenever you have a very high N. Okay, now let's break this down into its respective groups to see if our assumptions hold. So we have enjoy math, and see it put the label there, ST29Q04, so it's easier for me to remember what it is. Let's make sure we still have these plots in there. I want histogram and normality plots. Okay, let's give it a minute to run. If you're ever curious if it's running, there's a little dialog box at the bottom there that will say if it's running. Okay, nothing is missing within any of these groups, the PV1 math score, which means that it has broken this out correctly because we already knew that none of the scores were missing across the entire 65,000 students. And let's look at each different grouping variable. So students who strongly disagree. In other words, they do not enjoy math. Mean of 464, median of 458. So this is going to be a little bit more skewed than what we saw in the overall data set, which is perhaps helping make some claims about, could help us start to make claims about whether or not students who enjoy math at different levels have different math scores, because this group is going to be more concentrated on the low end if it's skewed to the right, unless it is due to a specific outlier. Standard deviation is a little bit higher, so there's more widely varying. Minimum 119, maximum 795. Skewness at kurtosis values look okay. Disagree, mean of 458, median of 450, so it is also a little bit skewed to the right, although less skewed, it seems, than the previous group. Standard deviation of 97, that is more similar to the overall standard deviation of around 95. Minimum 156, max of 803. Skewness at kurtosis values similarly look fine. In the agree group, we have a mean of 458 and a median of 453. So even less skewed. This one actually looks, those two scores are pretty similar to one another. A smaller standard deviation than in the overall group. And skewness at kurtosis values look okay. Minimum of 142, max of 768. And then we have the strongly agree group, mean of 457, median of 456. Those are almost identical. Standard deviation of 85. That is the lowest standard deviation of any of the groups. And skewness at kurtosis values look good. In fact, those are the closest to 0 of any other group, I think, meaning that they're closest to being normal. Minimum of 174, max of 789. Now, it's also important to keep in mind these grouping sizes. So the strongly disagree group is the smallest group, which is about 1,000 people smaller than the next smallest group, which is strongly agree. So we would expect smaller groups to perhaps have wider varying standard deviations than the bigger groups. These two groups in the middle are very similar in size, but still off by about 2,500 people, the agree group being the largest group. So there are fewer people willing to really say that they very much enjoy math or that they very much dislike math. Okay, tests of normality. All of them except strongly agree come out to a statistically significant difference from what would be expected to be normal. But remember, the high sample size is influencing that significant result. The strongly agree group still comes out unsignificant, meaning it does not vary significantly from what would be expected. But let's look at the histograms to see. Here is the strongly disagree group. You can tell that it is slightly skewed right, although overall it looks roughly normal. Disagree group also slightly skewed right. Agree group perhaps a little bit skewed right. And then the strongly agree group, which is remember the skewness at kurtosis values were closest to 0, meaning closest to being normal, and it is the most symmetric looking plot. Looking at the QQ plots, this does not look like things vary widely from what would be expected. The same thing here, although there is a slight movement away from the line, as opposed to here where it starts to move away but then comes back. This one also looks good, and this one also looks good. And then if we look at the box plots, things largely look symmetric, and what you're looking at when you're looking for symmetry in a box plot is distance from the median to the endpoints should be about the same, and also the whisker lengths should be about the same. You should also look for any extreme outliers. these are, even though these are technically outliers, they're clumped next to one another. So I would not be concerned about that. I'm looking for things that are points that are by themselves far away from all the other points. I don't see that here. Another thing to look for here is whether we should expect things to be different. If you look at their scores, the medians are almost identical across the board. Now remember, an ANOVA is not looking at the median, it's looking for differences in mean. So because things are not varying very much from being normal, we would expect the mean and the median to be relatively similar to one another. So I'm expecting when we run the ANOVA, it is not going to show much in terms of differences. It probably will not be a statistically significant result. But let's go ahead and check it and see. At this point, all of our assumptions appear to be met. No big differences from normality. And PISA did involve randomly selected individuals. It is a nationally representative sample within each country. And so I expect that independence is valid, although we have a little bit of an issue because students are nested within schools. So PISA data should be technically using a more advanced analysis that takes into account that natural structuring of students in classrooms. So that could present some issues, and what that does whenever that independence is not met is it inflates the standard error. And the standard error is used in the calculation of the p-value. And when those standard errors are inflated, it makes the likelihood of seeing a statistically significant result when you should not be seeing that more likely. So there is some potential issue here, but I want you to experience using a large scale database. So this is what we're going to use for right now. And if we were going to take account of that natural structure, there are also weights that we would use to attach to individuals, which we can talk more about later. All right, so general linear model, univariate. The dependent variable is PV1 math. The fixed factor is enjoying math. Under plots, I think we are just going to go with the basic plot that already is there. It will spit it out in a moment. Post-hoc, we're going to deal with this later. Let's see if we get a statistically significant result. Estimated means. Let's go ahead and do this because it will help us see that. That's what I meant by we'll see this in a minute. Options. Let's go ahead and have it spit out descriptive stats, effect size, power, and the one thing we haven't checked yet in terms of assumptions is test of homogeneity of variance. So we're going to get that. And let's continue. And click OK. All right, so one of the things I like to do whenever I click this descriptives is just look at the standard deviations. If there is big differences in standard deviations, then the test of homogeneity of variances is probably going to get kicked back and say these things are not equal. So if we look here, standard deviation of 105 all the way down to 85, that's a difference of 10. And because the differences in the sample sizes vary so much, this could be an issue. And if we look at the Levine's test of equality of variances, and remember, we're running this ANOVA to test differences in mean. So we're looking at the first row based on the mean. We see significance is 0. And if you forget what this test does, it tells you at the bottom. Test the null hypothesis that the error variance of the dependent variable is equal across groups. So this is saying that these group variances are too different from one another. They vary far away from what it would be if they were all equal. So we would be rejecting this null hypothesis that the variances are equal across groups, which tells us that there may be an issue here with these standard deviations. Let's look at the ANOVA results. The variable that we care about is this S29Q04. The F statistic is 7.9. That is rather large. And you see that the p-value, the significance column, is 0, meaning that these groups are widely different. However, remember that I said earlier that this could be being influenced by the fact that the sample size is so large. That is why we also look at this value, which we will talk about later in class. However, that value is interpreted like an r². And then if we look at the estimated marginal means, I thought apparently it didn't spit out the plot. That's okay. It looks like things are statistically significantly different. Let's actually look at the differences with the post hoc analyses, and I'm going to show you what I mean. It should be, here we go, compare main effects. Okay. All right, we want that to say compare main effects so that we can see the estimated marginal means. We can create a plot in a moment, but let's look at the post hoc tests. So we know that we cannot assume equal variances. So I'm going to go with this one, but I also want to check it against Tukey, which is going to, both of these tests are post hoc, meaning that they are going to dig down in and look at pairwise comparisons. So every pair of 2, so remember there's 4 groups, every pair is going to analyze, and they ensure that we're not inflating alpha by running multiple tests, so they fix that in the background for us. And I'm going to pick Tukey's just because I want to compare it and see how much of an impact the homogeneity of variances test that says they're not equal is having, because I'm not sure if it's just a result of sample size or not. Okay, and then the plot. Let's do this. Okay. So we already saw these results. Let's go down to the pairwise comparisons. So if we look across the significance, we can see that they are all 3 of the strongly disagree is extremely different from all the other groups. Agree and strongly agree, though, are not different from disagree. It looks like the only group that is different is strongly disagree. Let's see how close this is to that. Multiple comparisons here. If we look at the done it, we see strongly agree is different than all 3. We see disagree is different than strongly disagree. Agree is only different than strongly disagree. And strongly agree is only different than strongly disagree. So the done it is showing us the same results as what the Tukey was actually here. So it seems to be the case that the only group difference was with strongly disagree. So if we were going to write up a set of results, we might say something like this. First, we would need to describe center, spread, and shape of variables. I'm not going to put that here. And we would need to describe the assumptions, which we are unsure about whether or not there is homogeneity of variances. normality appears to be correct. So I would put those in there, that even though the test of normality showed that things were differing widely from normality, from what would be expected if it was normal, that all of the other evidence points to those variables and those within the subgroups, that PB1 math is roughly normal. Okay. So here we might say something like this. Results of a univariate ANOVA for, I would say, to examine differences in mean mathematics scores on PISA 2012 by student self-reported enjoyment level of mathematics. I'm not going to put that in there. Indicated that a statistically significant difference was observed. Now, we need to put in some information here to back up this statement. We need the evidence. So, we put the F-score, which the F-score comes from the overall ANOVA results, which in this case the F-score was 7.915. Degrees of freedom, and there are two of these, the numerator and denominator degrees of freedom. So those degrees of freedom are 4, 2, 7, 2, 1, and 3. And I need semicolons here. And then we need to say what the p-value was. And it was less than 0.001. And we should report the effect size. Okay. Post hoc analyses utilizing both Tukey, HSD, and what did we use? Did we use Dunnett? And Dunnett T3 indicated that the only statistically significant differences observed were between students who strongly disagree about enjoying mathematics and those and everyone else. And we could list the p-values and the confidence intervals for each of those differences. I'm not going to do that here, but that would be something you would want to do, is to list the p-values and the confidence intervals for each of those, and you could just do that in a small table, let's say, and say C table blank. Okay. And then you have to explain what that means. So in this case, I would say what you would interpret this to mean is that students who reported greatly disliking mathematics tended to score lower on the PISA 2012 mathematics assessment than those who did not. And we're making an inference beyond the data at this point because we're using a p-value. So it's important to state that on the PISA 2012 assessment, we can't extend out beyond that, but anyone in these 6 countries who was to take this test, if they strongly disagreed about enjoying mathematics, would be expected to have lower scores than those who do not strongly disagree. There could be lots of reasons for this. We can't speculate about that without doing some other things to analyze other pieces of data from PISA or elsewhere to try and draw connections about why this might be the case. All right, so that is what I would do here. And of course, whenever you explain assumptions, describing center spread and shape, make sure to include plots and other statistics as they are relevant. All right, see you in class.